All right, so this video is going to be on Diels Alder reactions. So those are basically the names of the two scientists that discovered it. And this is the mechanism right here. We're shifting pi electrons. And there's 3 arrows, as you can see, and those arrows are creating 2 sigma bonds and a pi bond as shown on the right. Okay. Notice that it forms a ring, a cyclohexene ring. Okay. And the way we do this is using a 1,3 diene as well as a dienophile. So it's basically an alkene, right? So a dienophile loves dienes. Oh, so, but yeah, that's what phile means, right? Like electrophilic, hydrophilic, etc. So notice the heat, the triangle is heat, and that's what gets this reaction going to form a cyclohexene ring. Okay, and you're always going to get a cyclohexene ring, and it always requires heat. Okay, so here are some key points, right? So basically, number 1 is formed or initiated by heat, and so heat is kind of ambiguous. Like to the everyday person, it's like, okay, boiling water is hot, right? But heat is room temperature as well. Okay, so it's all relative. And so this reaction can occur at room temperature for some things. Cyclohexene is formed. And so whenever you're kind of eyeballing these reactions, you want to always look for this, okay? Then that'll help you either determine if you made the right product or if you made the product from a Diels Alder reaction, okay? So breakage of, let's say, these 2 pi bonds right here circled in blue, and what happens is you break those 2 pi bonds and you form a new sigma bond, and that means that this process is exothermic, since pi bonds are weaker than sigma bonds. Okay, wait, hold up, let's take a look. I need to change that. My bad. So 2 pi bonds break and form 2 new sigma bonds. So sorry, that's what I drew above. And so that makes sense. It's exothermic since the pi bonds are weaker than the sigma bonds. Okay, and this is about by 100 kilojoules per mole. So that means that we're releasing approximately 200 kilojoules per mole, which is quite a bit. And number 4, we want to notice the red arrows are all moving together, right? And so that means that this reaction is, or the mechanism is, a concerted mechanism. Okay. Now, you guys know what this is. This is a cute little puffer fish. So this little puffer fish is well, you know that, maybe you know, maybe you don't know, but these blowfish are actually toxic if prepared the wrong way. So it's like in their organs, ovaries and liver, I think. There's a toxin in there if you consume it, and so the Diels Alder can actually be used to prepare that toxin. Okay, and so this would be the mechanism right here. What we ended up getting is this. It's not the toxin, but it's the start of it. Okay, so you can see that the cyclohexene ring is in that new product, and it came from butadiene, right? You don't want to watch me draw all that, but it's a tetradotoxin. Okay, and you can see this portion right here. It's a super crazy structure, right? It's a bunch of rings fused together. But this portion right here, I'm going to draw it in red on the side. This is actually called an adamantane. This portion, it's basically just fused 6-membered rings. And again, adamantane. This is actually a pretty common, or I don't know if it's super common, but it's pretty cool structure. I like the way that looks. And it almost, that's kind of like the structure of like a diamond if you expand it. But just wanted to point out that the tetradotoxin can be made using Diels Alder, right? So obviously there's plenty more to do to make that, but you can start it with a Diels Alder. Okay, so there are some rules to Diels Alder to make it work, right? So remember, this butadiene can actually rotate about that sigma bond, and we draw this plane in here, right? That makes it an S-cis conformation or an S-trans conformation when you get rotation about that bond, right? Now for Diels Alder to work, we need the S-cis conformation. Okay, that means that if it's rotating, it's obviously going to be in two different conformations, right? But we need it in this S-cis conformation to undergo the Diels Alder reaction. Okay, and so if we draw it like as such, the S-trans conformation in red, you can see that the shifting of the arrows doesn't really work out, right? Because the carbon that needs to make that new bond is like way over to the left, okay? And good thing that the sigma bond about that rotation, or the rotation about that sigma bond, is nice and easy. However, you can have them when they're fixed and there's no bond rotation at all. So like cyclopentadiene. Here, it's a 5-membered ring, and we do have that conjugated diene system in here, and it's fixed in the S-cis conformation. That makes this guy super reactive, okay? And because there's not some population of it in the S-trans and then some of it in the S-cis, right? It's always in the S-cis, therefore it's always ready to react. Now this bicyclic compound on the bottom, on the other hand, is always fixed in the S-trans conformation, and that means that this is never going to do a Diels Alder reaction, okay? It can definitely do other things, but it's not going to do a Diels Alder, okay? It's unreactive. So again, you need the diene in the S-cis conformation. And this, again, can just happen by simple bond rotation. But if it's stuck in that position, then it's going to react faster. Okay. So let's talk about electron withdrawing groups in dienophiles. Okay. What they do is they increase the rate of reaction. Now, why would this be? Okay. Let's first of all remember that the dienophile is the thing that loves dienes. So it's the alkene, right? And so this is a really basic alkene, ethylene on the left. And then we've got this one with the aldehyde functional group. And it's an electron withdrawing group because you have this delta positive, delta negative. You can also kind of create a resonance structure so that you have a negative charge on the oxygen and a positive charge on that terminal carbon. Okay, so it's withdrawing electron density. And some population of it kind of, or not some population, but it kind of looks like a positive charge to that electron-rich diene. And so if you were thinking of it as attacking that dienophile, then it's going to love to attack that electrophilic dienophile, right? It's more reactive because it's got a delta positive on that carbon, okay? And so it's more than happy to accept electrons to get the party started and start shifting pi bonds to create that cyclohexene ring. Okay, remember it is a concerted reaction, but it's got to start somewhere, right? So it is susceptible to nucleophilic attack again because it is electrophilic or delta positive because of the adjacent positive carbonyl that's bound to the more electronegative oxygen. All right, so I'm going to list some of these common dienophiles out for you. Some of them, I mean, we don't really need to know the names, but you'll probably just get used to it after a while. But we have just basically make note of the functional groups that are coming off of it. You can see we have an aldehyde, a ketone, an ester. This guy right here is fancy. That's maleic anhydride. It's got two, it's basically a ring, right? This guy right here, also super fancy. And then I'll throw a couple more in here for you. Let's see. So we could have a carboxylic acids on either side, or a carboxylic acid only on one side. Okay. So these are common dienophiles just because even like carbonyl groups are actually pretty reactive, right? So you can functionalize them after the fact, but the Diels Alder reaction moves nice and smoothly because it has the carbonyl group on it, which is an electron withdrawing group. Okay. Now, stereochemistry of the dienophiles after the reaction. Okay. So you can see the stereochemistry in terms of an alkene, right? So that's cis and trans, really. And if we have a cis or trans dienophile, then the stereochemistry is going to be retained in the cyclohexene product, okay? Or the Diels Alder product, whatever. Okay, so on the left we have a trans, on the right we have cis, okay? So the trans will yield a trans cyclohexene. Okay, and then the cis will also yield a cis cyclohexene. Now remember, if we're having functional groups or substituents on a ring, they can have cis and trans, right? So one's just poking out at us and one's away from us. That would be trans. And so let's take a look at this cis alkene or cis dienophile. If we were going to react with butadiene, we get this cyclohexene always. Now we got to jam two of those carbonyl groups on there, and we would draw them as such. Okay, those are on the same side of the ring, like pointed away from us, and so they are cis. Okay, now if we had that same ish dienophile but trans instead of cis, we would do the same kind of concerted mechanism, push those arrows all at the same time, get the cyclohexene, but now the carbonyl groups are opposite of one another. So one's pointed away, one's pointed at us, and you can get the isomers, right? So the enantiomers of one another, where we switch the wedge and the dash. Okay, so below we have in red the enantiomers as a product or as a result of reacting the diene with a trans dienophile. But then above, we had the super lame achiral meso compound. Okay, not really lame, but it just doesn't have, it has symmetry, so it's not an enantiomer. Okay, I actually kind of like meso compounds. Those are cool. Just, I don't know why. They're chiral, they have chiral centers, but they're not chiral overall. That's kind of fancy, right? This guy right here is maleic anhydride. Okay, so what's that going to look like? Well, just imagine all the stuff on the right of that alkene is gone, and then you could draw your cyclohexene, and then draw the rest on it. Okay, so just kind of like normal, but it's a ring. And what you end up with is a fused ring system, and it's also known as a bicyclic compound. Okay, now that bicyclic fused ring system doesn't look too tricky, right? You can I think you guys can handle that without even elaborating on it. But when we talk about endo versus exo addition, then it gets crazy. It's fun stuff though. So really the main point you want to remember is that endo is more stable and it's preferred. Okay, now when can you form endo versus exo products? So those are basically isomers as well, and they form generally when you have a cyclopentadiene reacting with some dienophile. Okay, now I'm doing a generic representation of this Diels Alder first, and then we'll elaborate with a dienophile with functional groups on it. Okay. And let me change that to red because it's electron rich, and then the blue will represent the dienophile. Okay, so what I want to do is highlight the carbons on the right, where it's kind of showing where they came from, right? So this is the easiest way to keep track of everything. The red is from the dienophile, the blue is from, the red is from the diene, the blue is from the dienophile. But where did that pink carbon go? Where does it go? It's not gone, I'm just not finished drawing yet, okay? Let's draw it from the side view, okay? So I'm pushing that pink carbon up, the diene and the dienophile react as normal, and we can kind of draw out our six-membered ring. Sorry, let me make it better. There's our ring, and then we have the pink carbon that was pushed up. It's still pushed up, okay, and it's kind of poking up on the top. And so if we're looking at the cyclohexene ring from the top, that's what the structure that we're looking at on the top. And then if we're looking at it more or less kind of from the side, that's the bottom structure. Okay. Now that's for the most part, that's how I'm going to draw it. And because this is the way you'll more easily identify endo and exo, or yeah, for the most part, that's the way you'll see it. Okay. Now that pink carbon, okay, is a bridged or I guess just in general, this compound is a bridged bicyclic system. And the pink carbon we would identify that as a single atom bridge. Okay, it's just bridging the two sides of that compound, that cyclohexene ring, if you will. And then we also have the blue carbons, for example. Those are also a bridge, and those are a two atom bridge. Okay, and you can look at the other side in the red. Those would also be like a two atom bridge. Okay. But the point is that we have bridges to kind of bring these two, the two rings together, or like kind of connect one side of the ring to the other. Okay. Now, when you have this setup where you have like this bridged cyclic system, that's when you can get your endo and exo. Okay. So let's say we have an R group on our dienophile now, and we heat that bad boy up with cyclopentadiene. We can have our R group being pointed down. That ring looks too good. I'm gonna have to copy and paste that way I don't have to draw it again. You know what I'm saying? You guys are gonna have to get some practice because your structure is gonna look horrible for a while. But I believe in you. Okay, when that R group is up, it's exo, and when it's down, it's endo. Okay, so when that R group is, I messed it up. Basically, that R group is underneath the ring. Are you serious right now? It's underneath the ring. Cool Joe Blue. I don't know why I feel like he should be called Cool Joe Blue. Maybe he is. Oh my goodness. I wasn't really sure which one to show you. Obviously, the top one is more appropriate, I think. But that bottom one, are you serious right now? Oh my goodness. The internet, man. I can't believe the internet is crazy. That's probably the best GIF I've seen in, I don't know, ever. So we're just having fun though, right? So basically, remember, endo is when that R group is underneath the rings, and exo is when it's pointed up, right? So, but why is endo more stable? Because we know it would be preferred if it's more stable, right? So let's draw our diene and our dienophile. The way they really do react, they're not side by side. They're actually kind of stacked on top of one another. And so I'm going to draw with dotted lines, kind of just to represent a transition state where bonds are being formed, bonds are being broken. And so all these dotted lines, that's really what that represents, okay? Now, if we look at it like this, remember that carbonyl carbon has a p orbital that's in that pi bond, right? And that p orbital is sticking up and down. And we also have a p orbital on that diene, the diene. And those p orbitals are actually, when oriented in this manner, can overlap, okay? And that overlap is kind of like, they're almost like creating a bond, right? And so that orbital overlap between the sp2 carbon of the carbonyl and the sp2 carbon of the diene, or the ring, it helps stabilize the transition state, okay? So that orbital overlap, those two p orbitals overlapping, kind of interacting with one another, that helps stabilize the transition state, and that's called secondary orbital overlap, okay? So if you're asked why is the endo more stable, or the approach more desirable, that's because of secondary orbital overlap, lowering the energy of the transition state. If it's lowering the energy of the transition state, then it's going to occur faster, right? And so that's why the endo is preferred. So what's going to happen? How does this explain endo, right? So let's say we did actually draw in those bonds. So that looks, it's going to look terrible, but I'm just for the sake of, just for the sake of the picture, right? We're going to rotate that. Now you can see how that R group is actually pointed down or underneath the rings. Okay. Do y'all even get it? What I'm saying right now? It's underneath. So like endo. Okay, cool. I'm good. I'm glad you got that. Sweet. So obviously the bridge, the single atom bridge, would has to kind of pucker or move upward to kind of minimize steric interactions or kind of improve the bond angles, right? That's Vesper theory. All right, so if we draw it where the carbonyl group or the R group in that dienophile is away from the ring, you can see that this p orbital is kind of, it is still pointed up and down, but there's no secondary orbital overlap, and so there's no stabilization of the transition state, and so this orientation or approach results in the exo product and is not necessarily favorable because of that higher energies transition state. Okay. And it's so, remember also, if we have a higher transition state energy, that's kind of this like higher activation energy, right? So it forms slower or maybe even not at all. Okay. All right. So this is some stuff right here. Retro Diels Alder. The Retro Diels Alder is, it's actually super fun to do. But at first it might seem kind of weird, crazy, also like mind-boggling, whatever. But it's basically retro, right? Back, like the past or back. It's working backwards to undo a Diels Alder. Okay. Now it's not like retrosynthetic analysis necessarily to see what you came from, but because it can actually be done in the lab. You can undo a Diels Alder in a laboratory. Okay. So let's say we have this particular bicyclic compound, and we draw our arrows just as we would before, but maybe the opposite way. Okay, we add some heat for sure. And what do we get? We get our diene and our dienophile, and that's exactly what would happen in the lab. Okay, we can undo the Diels Alder by heating it, and it's actually at least for like a cyclopentadiene one, which I'll show you in a second. That is a distillation. So it's a liquid when it's hot, and you can distill off the monomers because it really is a dimer. Okay. So let's take a look at this compound and really apply this retro Diels Alder to it and see what the dienophile and what the diene would look like. So first, you always want to look for that cyclohexene ring, right? And then you can just start by breaking those sigma bonds to create the dienophile, the alkene, and then make sure that you create your diene. Okay, or if you prefer, you can start by moving that pi bond in the cyclohexene ring. Okay, and then you end up with your diene on the left and then your dienophile on the right. And in this case, since they're both the CO2H, the carboxylic acid functional group is both dash, that means that the dienophile must be cis. Okay, because they're cis on that ring. All right, so let's try another one. This one's fancy. Okay, this one is a little bit more difficult, but you can do it. So let me see when I'm done drawing this. Okay, go ahead and pause the video and try it on your own. See what the diene and the dienophile are after a retro Diels Alder. Okay, so remember, we have to apply some heat to undo this and find our cyclohexene ring and then do those arrows backwards. Now, something I didn't mention before is that the arrows can actually go any direction, so clockwise or counterclockwise in the forward or reverse reaction. I just tend to do mine in this way. Okay, it doesn't matter though. So I highlighted the 4 carbons in red and the 2 in blue to represent the diene and the dienophile respectively. And just like that bridged compound was a result of a cyclopentadiene, so is this one. But this bridged compound has 2 chlorines on it because it does in the fused ring also, the bicyclic compound as well. And so, yeah, I mean, that's all you have to do is just make sure you're labeling all or highlighting all of your carbons just to keep track. That way you can draw out the final product in the end. I like to draw the alkene and the cyclohexene as first, and then obviously you know that comes from the diene, and so you have to get the two adjacent carbons in red, for example, and then the last two would be in blue in that cyclohexene ring. So let's do that again. Our pink bridge, we draw some arrows in the opposite direction, undoing things, and so we definitely got our diene. We have our pink bridge, right? And so that's going to be a cyclopentadiene. Now, if we draw our two blue carbons, now there's 3 other carbons, so that's going to create a 5-membered ring. Okay, sorry, I jumped the gun. So let me draw it the way it is pictured now. So we're creating that pi bond here, and then the other pi bond is skipping a bond, right? So it's adjacent to it. And if we were to redraw that, because it looks gross, it would look like this. And so what we end up having is 2 cyclopentadiene rings, right? They're the same thing. And that's just this compound right here is called a CP dimer, so a cyclopentadiene dimer, and that's because the cyclopentadiene undergoes a Diels Alder reaction with itself. Because yeah, it does have a diene, but one of those, if we just focus on one of those alkenes, then that's the dienophile. And this can actually occur at room temperature, and the process of heating it, distilling it into its separate monomers, or the cyclopentadiene, that process is called cracking. Okay, look at it's highlighted, it's in quotes, it's starred, it's got a little rectangle around it. You should probably remember that, right? Cracking is super fun to do in the lab. Just, I don't know why. Maybe it's not fun. It smells weird. It smells like pine trees kind of, but you know it's not good for you. So you're like, I don't think I like this, but I kind of do like this. But there you go. You can crack the cyclopentadiene dimer and then isolate the cyclopentadiene and then use it to do a reaction. And that's exactly what you do in a lab. And that's the significance of retro Diels Alder. That's really like the practical application, right? So I suppose you could undo something in another reaction too, or in another compound, but this is what we would do in the lab. We would take that cyclopentadiene dimer, break it up or crack it, and then do another reaction to get a new fused ring system, okay? Or the bicyclic bridged compound, okay? And this is what it would look like. So we would have the dimer on the left. We would have an arrow, reaction arrow. First, we heat it with heat. Then second, we hit it with a new dienophile. So we know that from the first step, we're getting a diene. And then the second step, we assign or we throw in a dienophile, right? So again, this is a distillation. I don't want you to think this is like a one-pot synthesis where you just heat it all together. I guess technically you might be able to, but that's not how it's done. That would just be a disaster in terms of purification. And so here we go. We form the diene, and then we react with the dienophile, and then we get a bridged compound. And we know that the left portion of that molecule is from the cyclopentadiene, and so these blue carbons represent the dienophile. And now we just need to make sure that we draw the rest of that ring, right? So it's a 6-membered ring, and then we've got carbonyls and an additional pi bond. Don't forget that pi bond on the far side. That's a common mistake. You want to make sure the only pi bond that disappears is the one that was representing or acting as the dienophile. Okay, so that's a lot, right? That was fun stuff, though. It's going to take some practice. So go ahead and hit up those homework problems, and then of course let me know if you have any questions. I know we're cruising through this material, but you got it.